First thing you take note of Lagrange theorem is that every coset has the same number of elements. So if you have coset consists of 4 elements, then every coset has 4 elements. Okay? If a coset has 2 elements, every coset has 2 elements. So the coset has the same number of elements. And what does the Lagrange theorem say? That okay, if H is a subgroup of G, then order of H, that means the size of H, must divide the size of G. Okay, this is what the Lagrange theorem say that. Okay, if H is a subgroup of G, then the order of H must be the divisor of order of G. So let's see a quick example here. Okay, so what does the Lagrange theorem say? Let's say, for example, suppose G has 35 elements. Okay, let's say G has 35 elements there, find a group there. So, can you find a subgroup? H of G such that the size of H equal to 2. You find a subgroup, they have 2 elements inside G. Okay, so what does the Lagrange theorem say? Lagrange theorem says that if H is a subgroup of G, right? If H is a subgroup of G, then the size of H must divide the size of G. Okay? The size of H must be the divisor of G, size of G. So is it possible now? Answer is no, right? Because H, the size of H is 2, the size of G is 35. So 2 doesn't divide 35, right? So answer is no. No way. Right? So there is no such subgroup. Order 2. Right? This is one way you can use, right? Because sometimes people ask you, oh, find a subgroup of order something for me. First of all, do you know there is or not? How do you find it, right? First of all, you have to know whether there is or not. So this one, no way. You say no. You cannot find a subgroup. You can find a set of 2 elements here. They are not going to form a subgroup. And remember, a subgroup must be closed, must have identity, must have inverse. Okay? With all these conditions, you say that it's not possible to form a subgroup this way. Okay, let's look at another example. Let's say size of G is 35. I don't know what is this group here, but I know that this group has 35 elements. Alright? Fine. Is there a subgroup? H such that the size of H equal to 7. Is there a subgroup H size of H equal to 7? It's not so sure, no? This is not so easy, no? Okay? Answer at this moment, don't know. Need to hunt for it. Right? At the moment, you have to do some hunting. Huh? You have to do construction, construct. Because Lagrange theorem said that if there is a subgroup, the size must divide. If the size don't divide, you cannot have a subgroup, right? So in this case, you have a H 7 element. Are you able to get this 7 element form a subgroup? It didn't say. Lagrange didn't say that, huh? It just say that. In order to form a group, this must be necessary but not sufficient. So you may not be able to find them. Okay? Lagrange theorem says that if you have a subgroup, the size of a subgroup must divide the size of original group. If you have a subgroup, huh? Alright? But first of all, do you know there is a subgroup of order 7? We don't know. Okay? So this gives you some quick introduction of Lagrange theorem. I want to introduce another term called the index of a subgroup. Okay, called the index of a subgroup. So index of a subgroup is the number of distinct left coset, in this case here, of H in G. So how many cosets are there? Count. Different ones, so different one. I count them, and this number is called index. Okay, so do you know how to find the index? Is there a way to count how many left cosets there? It's actually very easy. Because this is just, if you have a finite group, you just take the group size of G over size of H. That is the index of H and G only. Okay? So if you remember, just now I give you 2 examples. I think you have 2 examples about how many distinct left cosets. Let's try to verify whether this is true or not. So remember, just now in the beginning, I have Z6 is a group, H is a subgroup, 0, 2, 4. Where is the index of H? Index of how many left cosets are there? Distinct left cosets are 0 plus H, 1 plus H. These are the 2 distinct cosets. Okay? 2 distinct cosets, right? How come we know there are 2 of them and no more? Because G over H, size of G size over H is what? 6 over 3. It's 2, right? G equals X6, got 6 elements, H has 3 elements, 6 over 3 is 2. So you know there are 2 different cosets only. Right? 2 different cosets only. And happen that this coset form a group, we have a name for this. This is usually called G over H. And we find out that this G over H is isomorphic, actually the same group as Z2 just now. Right? The K table, same as Z2. Whereas, if I have G equal D4, symmetry of the square, symmetry of a square, where H is row 0, row 2 we have just now. So how many distinct cosets are there? So distinct cosets are G over H. What are the cosets? There are H there, row 0 H there, which is H there, and then row 1 H, mu 1H, delta 1H. These are 4 distinct cosets. Okay? 4 distinct cosets. How do we know there are 4 of them? You can use this. Size of G over size of H. Size of G is 8. Yeah, all together 4 rotation, 4 reflection. 8. Size of H is 2, and that's why I get 4.